Okay, guys, let us do work energy power. So now, remember the way the videos are structured. The first video that you're gonna see is going to be a recall and definition type video to help you collect marks, obviously, on the section. Now, an object of mass 10 kg is released at point A, which is 4 meters above the ground. It slides down the track and it comes to rest at point C. Now, state the principle of conservation of mechanical energy in words. Now, the principle of conservation of mechanical energy states that the total mechanical energy in an isolated system remains constant. Right? In an isolated system. Isolated system meaning that there are no external forces, right? There's no friction, there's no air friction, there's no force applied, none of that. Okay. Is mechanical energy conserved as the object slides down from point A to point C? So now the answer is for 1 mark. So the answer to that question is no. Now your explanation or your understanding now would be that the total mechanical energy was not in an isolated system. Why is that? At point A, we have height, but no velocity, right? This means now that we have potential energy and no kinetic energy. But when we reach point B, there is zero potential energy and zero kinetic energy. The object just stops at point B, right? And then since the mechanical energy is greater at point A and is zero basically at point C, mechanical energy was not conserved, right? It actually transformed from one form to the other, being most probably heat because there was friction along the track when it came to rest at point C. Okay, now using energy principles only, calculate the magnitude of the frictional force exerted on the object, as it moves along point B, C. Okay. Now, if we want to use energy principles, okay, we are going to have to use the work energy theorem, right? The work energy theorem, remember, includes non-consecutive forces in our equation. Okay, this would mean that F net would equal to the change in kinetic energy. So now we want to calculate the non-consecutive force, right? We want to calculate the non-consecutive force. The non-consecutive force in this case, because it was trying to stop the object, would be the frictional force. Okay. So now what I want to do, I want to first write down the last formula that we are going to use. So the last formula that we are going to use, we are going to say that work caused by the frictional force is equal to the frictional force, which is kinetic friction, right, by the change in distance cos of theta. Okay, cos of theta. Now, for us to calculate the work caused by the frictional force, we need to calculate the work done, right? We need to calculate the work done along BC. Okay, so what we have here, we're gonna say, so this is the final formula that we're gonna use. So now we need work, right? So we're gonna say work net, so this is the total work done, is equals to the change in kinetic energy, right? I don't want to add the four the 4 meters, right? Because remember, we are now, what we are trying to calculate now is the work done between point B and point C, as the question says. So now, okay, we can now calculate the change in mechanical energy, right? We could calculate the change in mechanical energy from point A to B. So we want to see the energy that was there at point point B. Okay, we want to calculate the mechanical energy that was there, the change in mechanical energy. So what we say is, okay, but wait, what am I doing? I'm confusing myself now. Work done by the non-consecutive force is equals to the change in kinetic energy plus the change in potential energy. Okay, so now we're gonna say mechanical energy at A, right? Mechanical energy will be EK at A plus EP, sorry, at A, right? So we have a half mass times velocity squared plus mgh. There was no velocity, so it's 0, plus the mass is 10 times 9,8 times 4 meters. That gives us a total of, put that in the calculator, my calculator here, so 10 multiplied by 9,8 multiplied by 4, which is 392 joules. So obviously at point B, as soon as we got to point B, we had 39 joules, right? Now, between point B and C, right? Mechanical energy between point B and C. That one there, because there was no potential energy, there was kinetic energy, right? So what happened there? So let's draw a line here, and then we say that the mechanical energy, or change in energy, in kinetic energy, EK at C minus EK at B. Now, this object was now grinding to a halt. Yes. So it was being carried by the potential energy that worked its way down, right? So now there was no velocity. So this means that this EK is 0 joules. Okay? Now, work final will equal to work total, will equal to work final minus work initial, which is 0 minus 392. That would mean that we lost 392 joules. Okay? Now, what did we say in the beginning? Okay, box like that, box like that. We said in the beginning we're going to use this as our final formula. So we're going to say work final is equals to the frictional force change in distance and cos theta. We have 392 joules. It was lost due to this frictional force over 8 meters cos 180. Okay, remember it was lost, so put in that negative sign. Then we're just going to put that in your calculator. You're going to say negative 392 divided by 8 multiplied by cos of 180 cos 180, put a bracket there, and then we get that the frictional force is 49 newtons. Remember, it's a force. Get that the frictional force is 49 newtons. So that is the magnitude of the frictional force between point B and point C.